Hi. Hello, everyone. My name is Balint. Together with my colleague Imre, we work at ARM. Thanks for joining this session. Our agenda will be to have a short intro about the project, about Rust and FFA. Then we will dive into some implementation details of the project. And after that, we want to share our experience about working with Rust, what we did like, what we didn't like. And hopefully at the end we will have time for some questions. So first, some background about the project. It started around 2 years ago when we decided that it would be good to learn Rust just as a hobby outside of work. And after learning the basics, we thought that since we are writing firmware at work, it would be nice to combine these two somehow. So we decided to write an SPMC, which means a Secure Partition Manager core, and it's defined by FFA, which is the firmware framework for RMA profile. We chose this component because we already had some expertise in this area. Also, it's a well-defined component that we could test in our existing environment. For example, with the secure partitions from the Trusted Services project that we also work on. We didn't have much spare time for development, so progress was slow. But last year it finally reached a usable state. So we decided to donate the code to ARM, and trustedfirmware.org allowed us to publish it. It's important to note that the project is in an experimental proof of concept state. It's not suitable for production use yet. Also, the future of the project is unknown. Currently, it's not on ARM's roadmap to give us the time and budget to continue working on this, but if there is interest from partners, probably this will change. Quick summary about Rust. It's a memory-safe language, which makes it ideal for writing security-focused software. Multiple companies have published statistics that most of the vulnerabilities are caused by memory safety issues, and using Rust can help to eliminate most of these. Code written in Rust can have similar performance to C code because most of the guarantees that Rust provides are checked at compile time, so there is no runtime overhead. Also, there is no garbage collector and so on. Cargo, it's the standard build system and the package manager for Rust. We will talk a bit more about this later. The Rust compiler uses the LLVM backend, so it has support for a large number of architectures. And also we want to highlight that in the last few years, many major software companies and projects started using Rust. And also more recently, there were some government regulations to encourage the use of memory-safe languages. So let's move on to FFA, which again stands for the firmware framework for RMA profile. On this diagram, you can see the structure of an A profile processor, and typical scenario is that we have some kind of secure application handling a biometric sensor or storing sensitive data that's running in a secure user space. So far, often these solutions were vendor-specific, and to communicate with it from the normal world, you had to have vendor-specific code in all of your components. FFA offers a solution for this by standardizing the software architecture for basically everything outside of the normal word kernel and applications. So your secure applications will run in a so-called secure partition, which is managed by the Secure Partition Manager core. Relaying messages to and from the normal world is handled by the Secure Partition Manager dispatcher. So FFA offers a standardized communication protocol for these components, which consists of a register ABI, memory sharing operations, component discovery, and so on. Also, it describes how to isolate these components from each other using the ARM architectural features. So in our talk, we will focus on the Secure Partition Manager, which is responsible for the compartmentalization of the secure partitions and the communication between these and the normal world. This can run in either a secure EL1 or EL2 if present, or even EL3. We will focus on the secure EL1 version because that's what we implemented. So let's continue with the implementation details.
Okay, so let's see how we implemented this in our SPMC. So in EL3 we have the SPMD. This is our SPMC in secure EL1, and we have the secure partitions in secure EL0. In the SPMC, we have a small startup code in assembly just for initializing the stack, the vector table, and for a couple other low-level initialization steps. Then we jump into the Rust code. Here, the first step is to load and configure the secure partitions. The firmware loads the SP packages from the FIP image at boot time and passes them to the SPMC. These SP packages contain an SP manifest and the actual SP binary. The SPs are configured based on their manifest. The isolation between secure partitions is achieved by using virtual memory mapping. Each SP has its own virtual address space, which is controlled by the SPMC. This is one of the reasons why it's critical to have a robust SPMC implementation to ensure the isolation between SPs. After loading the secure partitions, we configure the correct access rights for the code and the data segments and map necessary device or shared memories if it was requested in the manifest. After this, we switch to secure EL0 and start running the code of each SP. When the SP completes its boot phase, it sends back an FFA message to the SPMC. And when all SPs have been initialized, the SPMC will send another FFA message back to the SPMD. This completes the boot phase of the secure side, and the firmware can load and boot the normal world components. Okay, so at this point, the SPMC is ready to receive messages from the normal world through the SPMD. The SPMC has an FFA message handler component. This is responsible for forwarding the messages between the normal world side to the SPs or between different SPs. There are also messages which are for controlling the SPMC. For example, if the normal world wants to share memory with an SP, first it has to send a message to the SPMC about the memory sharing. Then if the SP accepts this memory, the SPMC will map the shared memory into the address space of the secure partition. We have some platform-dependent code. This is mainly the UART driver for debug logging and the interrupt controller driver. We wrap these into a platform abstraction layer, so later we can add new platforms without the need of modifying the rest of the code. The SPMC supports multi-core operation, but secure EL0 SPs are single core according to the FFA spec. This means that the SPMC can run two different SPs at the same time on different cores. Okay, so this is our example integration. Our goal was to do end-to-end testing between the normal world test applications and the secure partitions. We used ARM FEP-based RefC platform. It is publicly available. We run trusted firmware A in EL3, which implements the SPMD component. This is our SPMC in secure EL1, and we run the secure partitions from trusted services in secure EL0. These secure partitions are the reference implementation of the PSA services for A-profile CPUs. In the normal world, we have the usual components. We run Linux kernel in EL1, And in EA0, we run the test applications also from trusted services. This includes PSA, ACS as well. The test applications can communicate through a kernel driver, and with this setup, we have a communication channel through all these components, but logically between the test applications and the trusted services. And we were able to run all our tests successfully.
So next, we wanted to share our experience about working in Rust, some of the benefits that made our life easier during development. For example, it's a common scenario that we have a pointer, it's not initialized yet, so it is a null value. In some other part of the code, we accidentally try to dereference it, which causes undefined behavior. In Rust, references can never be null. So to indicate that something was not initialized yet, we can use this option type instead, which can have a none state or a some state, which encapsulates the actual value. And to access this value, you have to unwrap it from the option. There are multiple ways to do this, either by simply calling unwrap, which will cause a panic if the option was none, or you can do a manual check. But either way, it's not possible to do null dereferencing, so you won't get any undefined behavior. The Rust compiler tracks the lifetime and owner of variables, and this means that when a variable goes out of scope, its lifetime ends and it gets dropped. And also, the compiler doesn't allow any dangling references, so it ensures that reference doesn't live longer than what it's referring to. So this is another typical scenario from the project that we have typed something like this map buffer. In the constructor, we have to map some memory, save it into this buffer member. When we drop it, we unmap the memory, and using this function, we can get a reference to the otherwise private member. And here in this example, we get the reference, but this mapped buffer will go out of scope here, and it will get dropped. So if we try to use the reference here, this would be a dangling reference scenario, but the Rust compiler doesn't allow this, so this code simply won't compile. You get this error. Another nice feature that we ended up using a lot are the various collections. In most firmware projects, usually we have at least some kind of linked list implementation with some C macro magic. In Rust, there is no need to reinvent the wheel each time, because Rust provides a reliable and efficient implementation for all of these. Also, iterators were very useful, not just for doing simple for each loop, but for more complex filtering operations, or like iterating on two arrays at the same time. Of course, it's possible to implement all of these in C, but in our experience, it was less error-prone in Rust. And the noted means that these are available in bare metal environments too, so without using the full standard library. Traits are similar to interfaces. In our experience, it allowed better code structuring and readability. For example, typically in firmware projects, you have some kind of abstraction for different platforms. Using traits, we were able to express this explicitly. Rust has built-in traits for describing if an object can be safely passed or shared between threads, and the compiler prevents sharing non-thread safe objects between threads. So using these, it's possible, for example, to express that wrapping an object into a mutex can make it thread safe, and we can express this in a way that the compiler understands, so you don't have to write a comment that mutex is protecting this and this resource. Another example we have from our project is the secondary core initialization. So here, this is the code we boot on the primary core, and we create the main data structure describing the SPMC, and this is the code that we want to run on the secondary cores, and we want to access this SPMC somehow from the secondary cores. If we would simply pass this to this new context, then we would move the ownership and we couldn't access it anymore from the primary core. So Rust offers this atomic reference counting pointer instead, and by using this, we can thread safely share the same object with the secondary cores. Another common thing in firmware projects is to have some assembly files. Rust makes this easy too. There is no need to manually invoke the assembler from your build system. You can just use this global ASM macro instead. Also, the inline assembly is powerful. There are various other flags and details that you can provide here that we didn't show in this example. And finally, the cargo build system. It's standard, but it's not mandatory to use it. But it makes life easier. It encourages code reuse through the crates system. And if you're also using Rust app, which is the standard toolchain manager and installer for Rust, then cross-compilation will be also easy. You don't have to manually find and download your cross toolchain. You can just describe what you need in your project, and Rust app can handle that automatically for you. Over to Imre.
Thank you. Okay, so beside the many benefits of using Rust, we also had a couple of difficulties as well. The lifetime handling of Rust allocated objects can be difficult if hardware is involved. For example, in our translation table module, we had to do some manual lifetime handling because Rust is simply not able to see what's happening in the hardware. The Rust compiler enforces many things which can be difficult to handle sometimes during development. This is not a real drawback because at the end you will get a better, safer code, but it can slow down development. For example, if you define an explicit lifetime on a lower layer, you have to propagate it all the way upwards through different layers. The language is quite heavy and it has many features, and sometimes it is hard to decide what to use for which problem. Design patterns and typical solutions to problems are not widely available for Rust. C or C++ has decades of head start, so you can find many books and articles about the preferred design patterns. Okay, a frequent question about Rust is about unsafe. We went ahead and included a couple of slides about it. So there are cases when the compiler cannot ensure all of its safety guarantees. For example, when dereferencing row pointers. In this case, the programmer has to do all the necessary checks manually and then do the unsafe action in the unsafe block. This results in a contained and minimalized unsafe code. And the unsafe code is clearly marked because it can only happen in the unsafe block. This results in better focused review efforts because you only have to be really careful with the unsafe blocks. The general advice about unsafe is do not use it, but rather use an existing crate which wraps the required feature in a safe way. Now we are developing a firmware, so we cannot really avoid the use of unsafe because we had to interact with the hardware and with other software components. Still, only 2% of our current code lines is unsafe Rust. We have 6% of assembly, which is mainly the startup code, a couple of functions for context switching and exception handling. On the right side, you can see all the different reasons why we had to use unsafe. In the FFA messages, we get row pointers, so we had to do some row pointer reference. In the device drivers, we had to do some peripheral access to memory mapped peripheral registers. We have a couple global variables. This is mainly for the heap initialization. We had to do some interfacing with assembly code. And as I mentioned, we had to do some manual lifetime handling in the translation table module. This is all where we have unsafe Rust code lines. It is less than 100 lines. In a similar C project, you would probably do a row pointer reference in every other line. So I think we are pretty much on the safe side. So to wrap up our presentation, this is still an experimental proof of concept project. It is not ready for production, but we are happy to hear any feedback from you, and we will see where the project goes in the future. Still, we were able to have feature parity with the Securia 1 SPMC implementation in OptiOS. We were able to achieve our goal of running Securia 0 secure partitions and do a successful end-to-end testing. Rust clearly has many benefits, and we really enjoyed using modern language. As for future plans, we would like to make the code more robust and increase test coverage. We already have some unit tests where we use the built-in testing framework of Rust. We made some shortcuts in our FFA implementation. We would like to have a complete FFA feature set implementation. And this is a bigger one. We would like to investigate the possible deployment of the SPMC to Securia 2. This way, it would be able to run Opti or other trusted OS as a Securia 1 SP. The repository is publicly available on trustedfirmware.org along all the documentation and build and test instructions, so feel free to give it a try. Here you can find the FFA specification and the Rust language page, and you can contact us on the trustedfirmware.org mailing list or Discord, or here after the presentation. And that's all from us. If you have any question, feel free to ask.
Two questions. One, do you use it as a reference design to test FFA features and yes, an SMPC reference design? The second question is, what if you support notifications and if you support creating and destroying VM context? Thanks.
We don't use it for anything yet. So this is just a proof of concept for the testing of trusted services and other SPs. If we use the SPMC, that's part of OptiOS.
Yeah, and about the notifications, we don't have support for yet. This is what I meant by implementing the full FFA feature set. So, we are planning to add the VM create and destroy messages and so on, all the others which are defined in the specification.
Yeah, the VM create and destroy, that should be a low-hanging fruit. Well, it's a direct request with some flags. Yeah. For the notifications, that's a bigger challenge. But we are happy to do it. It just depends on how much time we have.
I have a basic question. how mature is the compiler first, and did you compare the data, the binary size in C version and Rust version?
Yeah, well, we compared it with Opti OS, but we didn't include it in the presentation because it wasn't a fair comparison, because Opti has many more features and you cannot really strip down just to the SPMC part. Yeah, but it was smaller, obviously.
Yes, but there is no magic happening. We thought that it's smaller mostly because this is built for this single purpose of the security of an SPMC, and Opti was an existing project where this SPMC feature was added later.
So have you developed everything from scratch, or you used some pre-built scripts available, like for ARM architecture or like that?
But the architecture-dependent part, we developed it from scratch. We use a couple popular crates for generic tasks, like
some handling of some packed structs,
Yeah.
some logging framework, stuff like this.
converting enums to row types and these generic reasons.
Excuse me. Just to follow on from that, what about the assembly? Did you borrow that from Hafnium or something else, or was that from scratch as well?
I think it
Well,
mostly from scratch.
Yeah.
There was not much to do there, just some basic MMU initialization.
ARM has this document about bare metal initialization of Cortex-A CPUs. So that had a couple examples of initializing the different exception levels.
Right.
And
But
context
stuff
switching.
like MMU setup that can be done in Rust code, and there's crates for that, is there? And, yeah.
The initial MMU setup is done in assembly before we
Yeah.
could go to Rust code, but after that point, it's just handled in Rust.
Okay.
Yeah, so all the transition tables and keep creating the tree of the descriptors is done in Rust.
Thanks.
That's where the unsafe was necessary.
Yeah.
Yes.
And I started over 3 times.
And to be fair, we don't have any kind of side channel attack mitigation, so that would increase the assembly side, but we didn't focus on any of these hardening efforts yet.
Thanks.
Okay, thanks for your attention.
Yeah. Thank you.